Hello and welcome everyone to our three-part webinar series entitled Maximize Your Building Automation System. Today you'll be watching part one of the series, Utilize Building Automation Systems to Troubleshoot in Real Time. This is a pre-recorded lesson made available to you on demand. Parts 2 and 3 of this series will be live on July 21st and August 4th respectively. Let's get started with part 1, Utilize Building Automation Systems to Troubleshoot in Real Time. My name is Miles Ryan with Questions and Solutions Engineering out of Chaska, Minnesota. Questions and Solutions is a commissioning firm and I work as a commissioning engineer. I spend a lot of my time working with building operators to improve the operation of their HVAC systems. And a lot of that time is spent working on building automation systems to troubleshoot issues that have been encountered. As an officer in the Air Force Reserve, I also serve as a mechanical systems instructor at the Air Force Institute of Technology. I teach continuing education courses to Department of Defense facility operations personnel on the topics of HVAC design and analysis, HVAC control systems, as well as energy management. I hope you find this lesson beneficial as you work to improve the operation of your facilities. For those looking for continuing education credits, you must watch the entire webinar. For those who paid, a quiz link was included in your Eventbrite confirmation email. Once you've taken the quiz and received an 80% or greater, a course completion certificate will be emailed to you. Next, I would like to thank our sponsors for making today's webinar possible. We are extremely grateful for their generous support of our online education. Before I get started, I would like to remind viewers to expand the screen for optimal viewing of the presentation. Additionally, several of the forthcoming slides have been made available to you as handouts. It is necessary for you to download and/or print these out prior to working through the troubleshooting exercises at the end of this webinar. All right, for today's program agenda. First and foremost, I'm going to introduce this concept of a BAS, or a building automation system. Building automation systems allow us to view how a HVAC system is operating in real time. Additionally, I'm going to talk about sequences of operation. A sequence of operation is essentially a narrative explanation for how an HVAC system is supposed to operate. So if we have an understanding of the sequence of operation, we know how an HVAC system is supposed to operate, and we have a building automation system which allows us to see how it is operating, we in turn can use that building automation system and that knowledge of how the system is supposed to operate to troubleshoot when acute issues arise. So I'm going to present to you a methodical troubleshooting approach, essentially a 6-step process that you can utilize when utilizing a BAS, or building automation system, to try to troubleshoot issues you're having on your HVAC systems. And then the end of the lesson, we'll have 5 troubleshooting exercises, hands-on troubleshooting exercises, which will allow you to apply this troubleshooting approach that I've presented. Building automation systems, what are they? Well, building automation system is essentially like the new age version of an HVAC control system. So what is an HVAC control system? Well, think about all of the components, all the HVAC pieces of equipment you have scattered across your facility. You might have a mechanical room that has an air handling unit or more than one air handling unit. It might have boilers, chillers, a bunch of pumps. On your roof, you might have rooftop units, maybe a cooling tower, exhaust fans. And then throughout the whole footprint of the building, you're going to have ductwork and pipes. And then in the conditioned spaces, you're also going to have terminal devices such as VAV boxes, fan-powered VAV boxes, or like baseboard fin tube radiation. And each of those components of your HVAC system essentially has one or more control loops associated with it. These control loops tell these components when to operate and how to operate. So a control loop could be depicted with this very academic diagram that I'm presenting here. Now I'm not gonna, I think it's probably best to give you an example to work through as we explain what this diagram is trying to show. Think of a space that is heated by some sort of baseboard fin tube radiation that's located along the exterior wall of that space. And there's a hot water control valve that's going to modulate how much hot water is being sent through that fin tube radiation, depending on how much heat is required by that space. So essentially, the space is the process plant. And what we're trying to control in that space, the controlled variable, would be the space temperature. Now, if we want to control the space temperature to a desired value, it's probably best that we measure it with a space temperature sensor. So we can measure that information and then send that information to a controller. Now, the controller is the brains of the operation. It's comparing that sensed temperature to some desired space temperature set point. And based off of whether or not the sensed temperature is above or below set point, it's going to send some sort of control signal to a control device. So for example, if we're below space temperature set point by a couple degrees, that controller might know to send a control signal in the form of a command being sent to a control valve to open up a bit more, to provide more heat to the space. As it opens up a bit more hot water flows through the fin tube radiation. That radiation puts off more heat into the space, and the space temperature rises and hopefully comes back to set point. So that's just a simple example of a control loop. Now, there's many components in an HVAC system, all of which have one or more of these control loops associated with it. What makes a building automation system different from some of the legacy control systems we see out there, such as purely electric or pneumatic control systems, would be the technology that that controller utilizes to make that decision. In a building automation system, the controller is essentially a computer. It's a digital microprocessor that is taking information such as the sense temperature, comparing it to a set point, and making a decision about what to do about it. So a building automation system is actually a collection of computers that are essentially scattered out throughout a facility that are working together to maintain the temperature and the humidity and pressure and what have you of a building. They're oftentimes called computerized control systems because, again, it is the controller in these control loops that is actually just a computer. The computer is dictating the operation of the HVAC system. There's many terms out there that are all basically synonyms. Building automation system, or BAS. Sometimes you hear these systems referred to as DDC, or direct digital controls, or EMS, energy management systems, EMCS, energy management and control systems, building control systems, or building management systems. And actually, there's probably a host of other acronyms out there that all essentially mean the same thing. Having computers control the operation of our HVAC systems can be a pretty powerful thing. So, for instance, all of the inputs, all of the sensed temperatures, pressures, and humidities that we have, all that information is being input into these computerized controllers. And so all that information is then going to be available in digital format. Additionally, all the software points, think of like the set points or the accumulated run times on equipment, things of that nature. All that information is going to be available in a digital format as well. And then all of the outputs, that's all the decisions that these controllers make that manifest themselves as commands to control devices, are also going to be in a digital format. So if you have all this information in a digital format, it's a very, very powerful thing. Computers can do great things when they have information available to them. So what can we do with all that information? Well, for one, all of these controllers scattered throughout a facility can share information with each other. So for instance, if you have that controller, which is dictating the control valve on that fin tube radiation, which we just talked about, if that and all of the other like controllers and all the other served spaces were communicating back with the controller, which is dictating the boiler operation, well, maybe if none of those fin tube radiations are calling for hot water, maybe we could disable the boiler in such instances. And maybe if one or two of those zones start calling for hot water, then we could enable the boiler in such situations. So sharing information between controllers can be a pretty powerful thing. It can allow for customized programming, which can increase the performance of how our HVAC systems operate. It can reduce wear and tear on our systems. It can also greatly reduce the energy being consumed by these HVAC systems. Additionally, having all of this information available in digital format allows these computers, this building automation system, to give us glimpses into how the system's operating by use of what we call graphics. So different graphic screens depict components of the HVAC system. They'll show a system diagram showing how all the physical components are arranged together, and then display all the vital information to help you as the building operator better understand what's going on in the system. And that's actually the bulk of what we're talking about today. We're going to talk about how to use graphics, which are displaying real-time information about how the system is currently operating to greater benefit, essentially to help troubleshoot when issues arise. Having all that information in real time is great, but also being able to log all that information on set intervals, maybe every 5, 10, or 15 minutes, is what we call trending. Now, if we have all this trend log data available to us, we can do a whole host of things. We can look back on how the system has been operating for the last 24 hours, or the last week, or maybe even the last year. And actually, the topic of part 2 of this webinar series will go into greater detail for what capabilities or what uses we can use this trend data for. And then lastly, we can perform pretty sophisticated alarming with these building automation systems. So for instance, we might just have some warnings if things are getting a little too hot or a little too cold in certain spaces, things of that nature, but some critical alarms such as the boiler is failing to enable. Well, maybe we could set it up where those alarms are sent as text messages or emails or phone calls to a building operator, whether they're at work or they're at home on a Saturday morning, because they probably would prefer to know that the boiler plant went down on Saturday morning as opposed to showing up Monday morning with all the water pipes frozen in the building. All right, let's go into some examples of what some of these graphics might look like. Here's a graphic of a VAV box, a variable air volume box with a reheat coil associated with it. So it shows a bunch of different information. We might see information about the damper. It's a modulating damper, so it's telling you the position of the damper. It's telling you the desired airflow or the airflow set point at this moment in time, the current airflow. So we're going to have a airflow measuring device in there as well that's actually measuring the airflow. Here is telling us the size of the box. Over here, we're talking about the command being sent to the reheat valve. It looks like this guy's being commanded 100% open. Sometimes these VAV boxes have a discharge air temperature sensor that's giving us the temperature of the air leaving the reheat coil and being sent to the space. And then on this particular one, there's just a bunch of other information available as well. Now, these graphics are usually customizable. So you may have VAV box graphics for your facility that don't have nearly as much information as the one shown here. But this particular facility that I've been working in, they opt to have quite a bit of information being displayed for each VAV box graphic. Here's another graphic of an air handling unit. So it shows the physical arrangement of all the major components of an air handling unit. The supply, the return fan, the outdoor air damper, return air damper, relief air damper, the filter rack, the heating coil, cooling coil, as well as all the information which show how the system's operating. What speed is that fan at? What's the temperature at various locations in the system? What position and command is being sent to all those dampers and control valves, things of that nature. Here's another graphic for just a simple makeup air unit. And here's a graphic for a chilled water system. It shows the chiller. It shows the associated chilled water piping and pumps, as well as temperatures and other information. So a building automation system, by use of graphics, is a great tool. It helps you look to see how the system is operating. And as we'll show here in a little bit, it can help you in troubleshooting issues. However, it's a tool. It should not be your only tool, but it's a very effective tool only if the information that's being presented on the building automation system graphic is correct. So if you have faulty information being provided to the automation system, the automation system's graphic is going to be incorrect as well, and just give you a bunch of red herrings and make it very difficult for you to navigate and understand how your building is actually operating. What I'm getting at is if you have failed sensors or uncalibrated sensors, then the information that they're providing the automation system is probably not the most accurate, and the information being displayed on the graphic is also not going to be that accurate. Additionally, you might have this phenomenon called mismatch sensors. So right here, we showed the chilled water supply temperature at 45 degrees Fahrenheit. What if you looked at this graphic? What if you looked at this graphic and it said 145 degrees Fahrenheit? Well, that might be an indication of a failed sensor or an uncalibrated sensor. Or it might be an indication of we're not actually displaying the temperature of the chilled water supply temperature. Maybe we're accidentally displaying the temperature from the boiler system, the temperature leaving the boiler or returning to the boiler. That'd be an example of a missed map point. Information being displayed on the BAS graphic in the incorrect locations, which can really make it confusing when you're trying to understand the operation of your system. So what I'm getting at is the building automation system is a great tool. When it's first installed or expanded upon during some sort of capital improvement project, you needed to make sure that proper checkout has been done to make sure that it's displaying the correct information. Now that checkout should be done by a temperature controls contractor who would be installing such a system. Some building owners opt to have a third-party commissioning firm come in and check over the stuff and validate this as well. That's what my firm does. So that's where a lot of my experience comes from when it comes to building automation systems, kind of checking out other people's work. But additionally, as you move into the operating phase of a facility, you got to make sure that as sensors fail or become uncalibrated, they get replaced or get calibrated. Or if other devices fail, we got to work to get those things replaced, make them a priority, because otherwise you're going to come to a building automation system and you're going to have a bunch of information that's either not correct, or you're going to have a bunch of devices that are inoperable and cannot be controlled by a control system. It can be very, very difficult, and essentially the effectiveness of your building automation system goes to zero. So make sure you're being the squeaky wheel, asking for funding to make sure these components are being replaced so your automation system is being utilized to the greatest effect. Let's talk about this concept of sequences of operation. So a sequence of operation is essentially a narrative explanation for how a system is to operate. Where would you find these narrative explanations of how a system is supposed to operate? Well, from a construction project, they might be available in the design drawings or specifications from the design engineer. Or hopefully a more accurate version of the sequence of operation, the sequence that was actually programmed during installation, would be available in the O&M documentation or closeout documentation from a project. I'm talking record submittals or record shop drawings from the temperature controls contractor should have an accurate explanation for how the system was actually programmed to operate. Let's show you an example of what this might look like. So let's go back to that baseboard fin tube radiation example. So this is a sequence of operation I took from a project that I literally just went and tested some fin tube radiation sections out 2 days ago. And this is the sequence of operation that the temperature controls contractor provided to me. The radiation valves will modulate to maintain room temperature. When the room temperature falls below set point, the heating valve will modulate open. That makes sense. When the room temperature rises above the set point, the heating valve will modulate closed. That should make sense as well. The set point, which they're controlling to, the room temperature set point, will be 65 degrees during occupied periods. And then during unoccupied periods, nights and weekends, we're going to reset that value to 55 degrees Fahrenheit. And also, there's an alarm associated with this. When the room temperature falls below 50 degrees, an alarm will be sent to the building operator. All right, sequence of operation. It's very important that you understand the sequence of operation for the system that you're trying to troubleshoot. It's a prerequisite, really, because if you don't understand how the system's supposed to operate, how are you going to be able to tell that the system's not operating correctly? Now, some things such as fin tube radiation, it might seem obvious how it's supposed to operate, but actually there can be a lot of variations even on fin tube radiation for how they control this particular valve. Maybe that valve modulates to try to maintain temperature right at set point. Maybe that valve is two position where it'll open if the temperature drops below set point, and it will only close when the temperature rises 2 degrees above set point. There's more than one way to skin a cat, especially when it comes to complicated air systems, which we'll talk about next. You might have 5 air handling units serving your facility. They might all look the same, but for various reasons, they might all be controlled drastically different. So you need to understand the sequence of operation for the specific system you're trying to troubleshoot. All right, so let's talk about a sequence of operation for what I'm going to call a variable air volume with reheat system configuration. So here's a diagram of what such a system might look like. Over here, all these components I'm kind of circling, those are going to be an air handling. That's all going to be components of the air handling unit. You have a return fan, a supply fan, a couple dampers, pre-coil, cooling coil. Essentially, the air handling unit is mixing outdoor air and recirculated air and controlling it to some sort of supply air temperature, keeping it at some constant supply air temperature set point, which is then made available to downstream spaces. Now, each downstream space or zone is going to have supply ductwork being taken off of the main ductwork here. And in that supply ductwork leading into zone, you're going to have a VAV box or variable air volume box. And in this case, we have a reheat coil also associated with that box. So in that VAV box, you have a damper, which can modulate the amount of cool air being sent into a space when the space is calling for cooling. And then you have a reheat valve, which can modulate hot water going through the reheat coil to raise the temperature if need be as part of some sort of heating sequence for the space. Now, this type of system configuration is going to have more than just one zone. I'm just showing you one zone here to help you better understand how the system all fits together. But as we go over here, there could be 10, 20, 30 zones on this particular system that are served by this air handling unit. All right, so air is mixed with the space, and we return air through the return grill into the return ductwork. We're going to mix that air with return air coming from other spaces, send it through a return fan. That air, some of it's going to either be exhausted out of the building, or some of it's going to be recirculated through the return air damper, and then mixed with some quantity of outdoor air. So there's a lot of different components going on here. So I want to talk about what a sequence of operation might look like for a system like this. And again, I said there's a lot of different ways in which these type of air handling units and systems can be controlled. But I'm going to present one way to you, a more conventional way, and we're going to use this sequence of operation I'm presenting to you here in the upcoming troubleshooting exercises at the end of this presentation. Okay, let's get started. So the outdoor air damper, return air damper, and exhaust air damper, they're all going to modulate simultaneously to maintain supply air temperature at set point when the economizer is engaged. The economizer disables when the outdoor air temperature is at 70 degrees Fahrenheit. So what that's saying is this air handler, its primary job is to supply air at some temperature. All right, how it gets that air to a temperature, there's a couple of things at its disposal. It's got these dampers, it's also got this preheat coil and cooling coil. But let's talk about the dampers. If the outdoor air temperature is below 70 degrees outside, we're going to presume that there's cool air available outside. So instead of running the chiller and the chilled water pumps, we're first and foremost, we're going to just bring in higher quantities of outdoor air if we're not meeting our supply air temperature set point. If our supply air temperature is above supply air temperature set point and the outdoor air temperature is below 70 degrees outside, first and foremost, we're going to bring in higher quantities of outdoor air to see if we can't reach set point. If we can't reach set point, then great. We don't have to run the cooling coil. If we go to 100% outdoor air and we still can't meet set point, then we'll have to run to the cooling coil. We'll have to open the cooling coil's control valve, which we'll talk about here in a second. Additionally, as the outdoor air temperature continues to drop outside, we're going to be requiring less and less outdoor air to be able to maintain supply air temperature at set point. However, we're not going to let the outdoor air damper ever go completely closed. No, we're going to set a minimum position that's going to correlate to a minimum amount of ventilation requirements, because we got to make sure that we're always bringing in enough air to meet the ventilation requirements of this space. So this last sentence here, during occupied hours, these dampers will not allow outdoor airflow to drop below the minimum ventilation requirements. Now, what happens if the outdoor air temperature gets above 70 degrees? So say it's 75 or 80 degrees outside. In those instances, we're not going to be wanting to be bringing in higher quantities of outdoor air. Rather, when the outdoor air temperature is above 70 degrees, we're going to revert back to bringing in just the minimum amount of outdoor air. Okay, let's talk about the preheat coil and cooling coil. The hot water and chilled water control valves will be modulated when needed to maintain the supply air temperature at set point. They should never be opened at the same time during normal operation, but the chilled water control valve may be opened at the same time the economizer is engaged. I kind of just talked about that. There might be instances when we're bringing in 100% outdoor air and also running the cooling coil. Now, if the heating coil control valve is ever opened, that means it's pretty cold outside, and our outdoor air damper has already gone to minimum position. Now let's go back and talk about these dampers for a second. I said that these dampers modulate simultaneously. That's not always the case in all systems, but for this system, I'm going to say that if we tell the outdoor air damper to go to 60% open, we're also going to tell the exhaust air damper to go to 60% open, and the return air damper is going to get the inverse of that. The return air damper is going to go to 40% open. Another example, if we tell the outdoor air damper to go to 90% open, the exhaust air damper also is going to go to 90% open, and the return air damper is going to go to 10% open. Okay, so we have these dampers. We have a control valve on the preheat coil and a control valve on the cooling coil. 3 different mechanisms that are going to be operated kind of in sequence to maintain supply air temperature at set point. So let's talk about what's going on at the zone level. The VAV box has 2 components. That has a modulating damper and a reheat valve on the reheat coil. So the VAV box damper will modulate to reduce the airflow when the space temperature falls below set point. So essentially, this damper is going to modulate when this space is calling for cooling. It's going to modulate the amount of airflow being sent into the space when this space is calling for cooling. It's actually modulating to maintain an airflow set point, and then we in turn measure the airflow, but that airflow set point is going to be reset based off of how much cooling this particular space needs. Now, if we keep on falling below set point, we're going to keep on reducing the amount of cool air that's being sent into the space. So we're going to keep on reducing the airflow set point. However, we're not going to modulate it until this damper is fully closed. It will not modulate below its minimum airflow setting during occupied hours because we need to ensure that fresh ventilation air is always provided to the occupants in that space. So if the space temperature continues to fall and we go to minimum airflow, the damper will just maintain that minimum airflow, and then we will begin to open the reheat coil's control valve to warm the air being sent into the space. Okay, so if that box, that VAV box's damper is modulating, that's going to have effects on the system elsewhere. Changes in downstream VAV box dampers will affect the static pressure in the supply air duct. This is the supply air duct. And we know if we're closing this damper here, that's going to drive up the pressure in the supply air duct. So closing VAV box dampers will raise the pressure, which will be an indication that less airflow is needed, and the supply fan can slow down. So the supply fan right here, its speed will modulate to maintain the static pressure at a set point in the supply duct, but the speed of the supply fan will never be allowed to go below 15 Hertz in frequency. Similarly, we're going to modulate the speed of the return fan. However, the return fan will be modulated to maintain a slightly positive building pressure in relationship to the outdoors. So we're going to have a differential pressure sensor, which is measuring the differential pressure between the inside of the building and outside of the building. And we're going to want to keep that building slightly positive. So we're going to have a set point we compare it to, and we're going to modulate the speed of that return fan accordingly. But again, we're never going to let it go below a minimum speed of 15 Hertz. Now this sequence of operation, this slide right here has been made available to you as a separate handout. So I would recommend that you download it, print it out if need be, especially when we start walking through some of these troubleshooting exercises. It's going to be very important that you understand the sequence of operation because, again, it's kind of a prerequisite to understanding the sequence of operation for a system is really a prerequisite before you could ever effectively troubleshoot such a system. All right, so I spent a lot of my time troubleshooting HVAC systems. And I talked to a lot of people about the methodology in doing so. And you often hear people say, when troubleshooting, you gotta look for the most obvious thing first. For instance, if you get a cold complaint from a space, you should first and foremost go ensure that the boilers are operational. I actually disagree with this approach. I mean, surely, if the boiler had been disabled, this approach may identify the root cause very quickly. However, there are many other potential reasons for a cold complaint coming from the space. If looking to see if the boiler is down is the only tool in your toolbox, you might be left high and dry when the boiler is found to actually be operational. So a more methodical approach is required to narrow in on the root cause. And that's what I'm going to present to you here. So this is a 6-step approach. First step in troubleshooting an issue would be to know the sequence of operation. All right, so say someone calls in or you get some sort of alarm on your automation system saying something's going haywire. Before you can really troubleshoot it, you're going to need to know the sequence of operation. All right, and now before you send a technician out to investigate, to actually physically go to the space or to the location of the system to investigate, you should probably pull up the BAS first, because if you pull up the building automation system first, it'll help you narrow in on what the root cause is. Maybe you'll be able to figure out what the root cause is just by looking at the automation system. Or if anything, you'll be able to narrow it down to just 1 or 2 items before you send out a technician. And you're gonna be much more effective at troubleshooting systems if you utilize your building automation system first and foremost before just blindly walking into a space trying to figure out what's going on. So step 2 in this methodical troubleshooting approach would be, if possible, see if you can't validate the complaint or observation on the building automation system. So if someone says, hey, it's too hot in my space, we'll pull up the automation system and see if that's what you're reading as well. What's the temperature of the space showing on the automation system? Or you might have an alarm come in on the automation system saying, you know, the pressure is too low in a hot water system or something to that effect. And you can maybe pull it up and see that information and validate maybe that alarm threshold was inappropriate, but you can at least validate if the complaint or observation is legit. Step 3 would be, ask yourself this question: is the variable in question being controlled for? So for instance, if we have a cold complaint coming from a space, the variable in question would be the room temperature. Do we actually have a thermostat? Are we actually controlling for the temperature in that specific space? Or is the thermostat actually located in an adjacent space? And that particular office in question is actually not being controlled for directly. Not being controlled for directly, is there another variable out there that correlates to it? An example I just provided, yeah, we'd have the adjacent space's temperature, which is on the same thermal zone, being served by the same VAV box. All right, so step 4 would be, investigate that specific control loop. Ask yourself these questions in this order. Is the set point appropriate? Is the controller response as expected? And then, is the manipulated variable as expected? Now, manipulated variable is kind of an academic term, and it actually goes back to that control loop diagram I showed on like the 4th slide of this presentation. And it'll make more sense what a manipulated variable is as we work through some of these examples. So I'm not gonna go too deep into that at this point in the presentation. So if all of that checks out, maybe you can ask yourself the question, what other variable could be causing this issue? Once you figure out what that other variable might be, you can repeat steps 3 and 4 for this variable. And step 6 is just telling you, keep doing this over and over. Keep peeling back the onion until you find something that is out of place. And then you'll find something that's out of place, and maybe it'll be obvious what's going on. But if anything, it will help you narrow in and send a technician to respond to that specific location to more effectively troubleshoot on their trip to the site or their trip to the building or the portion of the building. Okay, so now we're going to go into some troubleshooting exercises. But before we can really troubleshoot an issue, issues on an HVAC system, yes, we need to know the sequence of operation, but we also need to know some important information about how the system was actually designed. So, for instance, on the system we're going to be looking at, the chilled water supply temperature, the temperature of the chilled water leaving the chiller when the chiller is operational, was designed to be 44 degrees on like the hottest day of the year. Now, there might be instances when we raise that set point above 44 to maybe save some energy, improve the efficiency of the chiller on more mild days. But on design days, when it's like really hot outside, we probably should be operating at 44 degrees Fahrenheit. Similarly, our hot water system and all of the components, all of the heating components, reheat coils, preheat coil, things of that nature, they were all sized and selected for 160 degree hot water supply temperature. Now, if you have like condensing boilers, there might be instances when it's appropriate to operate at a lower temperature. On more mild days, you might get by with 120 degree hot water supply temperature. But on the coldest day of the year, to effectively heat this building, you're going to need 160 degrees Fahrenheit. On the air side of things, the supply air temperature, well, the system was designed to have a 55 degree supply air temperature coming out of the air handling unit on those coldest days, on the hottest days of the year when the greatest amount of cooling is required. Now, again, more mild days might be appropriate to raise that set point, the supply air temperature coming out of the air handler. However, just know that the system, if operating correctly, should be able to meet the cooling requirements of the space on the hottest day of the year at about 55 degrees supply air temperature. All right, so the VAV box that we're going to be looking at, that's the VAV box that's serving a particular space. The one we're looking at has some airflow settings that are coming from the design engineer. They said that they never want, during occupied hours, they never want the airflow to go below 130 CFM because they want to provide sufficient amount of ventilation air to the occupants. But they never want more than 1340 CFM. That's the design airflow. So they say on the hottest day of the year, fully occupied space, 1340 CFM of 55 degree air will be sufficient enough to cool the space. And then just some gee whiz about the climate we're working in here. On this particular system, the cooling system was sized for 91 degree Fahrenheit outside air temperature. And the heating system was sized for a 7 degree outdoor air temperature. All right, so let's go into these troubleshooting exercises. The first one, I'm going to walk you through. I'm going to walk you through how to apply that 6-step methodical troubleshooting approach. And then exercises 2 through 5, I'm going to present the issue and then allow you to pause the presentation, apply the methodical troubleshooting approach yourself, and then once you think you figured it out, hit play and I'll give you the solution. All right, before we go into troubleshooting exercise number 1, let me explain what we're looking at here. So this diagram should look very similar to what you've already seen. This was the same diagram I used to explain how an VAV with reheat system configuration operates. However, now I'm using that same diagram to represent a graphic screen on a building automation system. So think of what you're looking at here is a graphic screen on a building automation system. So in addition to just the components, it has a bunch of other key information being displayed for you. Over here on the left-hand side, you have the chilled water supply temperature, chilled water supply temperature set point, chilled water pump speed. You have a hot water supply temperature set point, hot water pump speed, and then the mode in which the air handling unit is operating. So it's operating in occupied mode right now. You also have different temperatures in the system. So the return air temperature, which looks like they must have a sensor on the downstream side of the return fan. That's measuring 82 degrees right now. You'll have your outdoor air temperature, mixed air temperature, supply air temperature, room air temperature. Back at the air handling unit, you have percentages for the different dampers. The outdoor air damper, 100%. That's a command. That's not necessarily the position, but that's the commanded position that the automation system is telling that damper to go to. There are some dampers out there that have position feedback, where you see both the command and then the actual position. However, it's very common to not have position feedback on dampers, and instead all you have on the automation system is what the automation system is telling the damper to do. Same thing on the control valve for the heating coil and the cooling coil. Those are the commands being sent to those respective valves. For your supply and return fan, you have the speed at which these fans are operating at. You have your supply air temperature and your supply air temperature set point. Over here, this is supply air static pressure and supply air static pressure set point. Again, that's part of that control loop which controls the speed of the supply fan. Now, for this particular zone, you have the room temperature set point, the occupancy mode of the zone, and then back at the serving VAV box, you have other information as well, such as the command that's being sent to the reheat coils valve. You also have the measured airflow as well as the airflow set point. Now, on a real world building automation system, all this information would probably be displayed in 2 or more different graphics. You might have a graphic just for the air handling unit, and then each of the served zones would have their own graphic. Now, just for simplicity and to help make this presentation a little bit more intuitive, I've opted to show one of these single zones in conjunction with the air handling unit. Okay, so let's get started with troubleshooting exercise number 1, now that we have been acclimated for what we're really looking at. The situation is this: it's springtime. The chiller has been disabled for winter and it's still disabled. So maybe they didn't have glycol in their system and they had to drain the chilled water pipes. They hard disabled the chiller for winter and they haven't got around to starting it back up yet because it's early spring. Now the issue is the space temperature is just too hot. All right, now I've also made 2 other handouts available to you, or 3 handouts in total. The sequence of operation slide has been made available to you. The troubleshooting exercises key information slide has been made available to you, as well as that 6-step methodical troubleshooting approach. So we're gonna walk through that methodical troubleshooting approach now. So step 1, again, it's a prerequisite to know the sequence of operation for the system we've been working with. Now, we're gonna press on because I know the sequence of operation, but in the exercises ahead, if you need to pause and review the sequence of operation slide, go ahead and do so. It is a prerequisite before you can really do anything else. Step 2, if possible, validate the complaint or observation on the building automation system. All right, the complaint must have came from someone in the space saying, hey, it's too hot in here. So we look at here and we say, the temperature is 81 degrees Fahrenheit. It must be too hot in there. That's pretty uncomfortable. I'd be uncomfortable at 81 degrees Fahrenheit. So it looks as though it's been validated. Step 3, is the variable in question being controlled for? Well, the variable in question would be the space temperature for room 215. Is that a controlled variable? Is that something we're actively controlling for? Well, yes, it is in this case, because we have an associated stat with an associated set point, and we have a dedicated VAV box with some components in it that is trying to maintain that temperature at said set point. So let's investigate that control loop, step 4. Step 4.1, is the set point appropriate? Space temperature is at 81, set point is 73. I would say that set point is appropriate, yeah. Is the controller response as expected? Now, what would the controller response be here? So the temperature is 81 degrees. We're well above set point. So we're probably calling for like full cooling at this point. So the expected response from the controller, I would expect to see the reheat valve being commanded closed, which it is. And I would expect that the box to be calling for maximum airflow. And as you know, for this particular box, the maximum VAV box airflow is 1340 CFM. Okay, so step 4.2, is the controller response as expected? Yes, it is. Is the manipulated variable as expected? So the manipulated variable in this case would be the actual airflow. Like, are we getting the airflow that we wanted? Well, we're a little short, 1320, but I can tell you from experience, being 20 CFM short in this particular scenario, that's not the culprit here. That's not going to make or break. That's not going to close the distance of an 8-degree temperature air from your set point to your space temperature. So I would say for all intents and purposes, our airflow essentially is tracking on set point. Okay, so everything's checking out so far. Let's go to step 5. What other variable could be causing the issue? Okay, so we're trying to cool this space. So what affects cooling? The amount of airflow and then the temperature of the air being supplied. So we're getting all the airflow that we want. Are we getting the temperature of the air cool enough? Is the temperature of the air being sent to the space cool enough? Well, we see down here that set point's 55, but man, we're at 72. Something seems a little off there. Well, let's see if we can figure out why it's at 72. All right, so we got to go back to step 3. Is that variable in question, now the supplier temperature, being controlled for? Yes, we know from the sequence of operation that there's several different things which are controlling the supplier temperature. We got these dampers, we got the heating coil and the cooling coil. All right, so let's investigate those various control loops. Is the set point appropriate? Is the supplier temperature set point of 55 appropriate? Yes, it is. That's what the system was designed for. Is the controller response as expected? Well, there's 3 different kind of control response we could expect here. Since we're so far above set point, we'd expect the cooling valve to be 100% open. We'd expect the heating valve to be 0% open. Everything's checking out there. And we would expect that the economizer, since it's 55 degrees outside, would probably be trying to bring in 100% outdoor air, which appears to be the case. Outdoor air dampers command to 100, return air dampers commanded to 0. All right, step 4.3. Is the manipulated variable as expected? All right, so for each one of those 3 control responses, is the system, are we getting what we expect out of it? So if we open the cooling valve 100%, we'd expect a big drop in temperature across the cooling coil. So the manipulated variable would be like, you thought of it like chilled water flow rate. Well, apparently that's not happening because the mixed air temperature upstream is 70 and downstream is 72. So we're not really cooling the air off, but that could be expected because again, this chiller is still disabled from the winter. Look over here, chilled water supply temperature is 60 degrees and the pump is off. Even though the valve's open, the pump is off. We're not actually pushing in chilled water. Well, maybe the heating valve is leaking. Maybe that's the culprit. Well, the heating valve's at 0. Is it leaking? I don't know. We have a mixed air temperature entering at 70 degrees. We have a supplier temperature downstream of the supply fan at 72. We do have a temperature rise there, but that 2-degree temperature rise could probably be associated with just fan heat from the supply fan itself. So I really don't think we have a leak coming from the heating coil at all. All right, well, let's talk about those dampers. Those dampers are trying to bring in 100% outdoor air. So the manipulated variable could be thought of as the percentage of outdoor air. So if you think, if we're bringing in 100% outdoor air at 55 degrees Fahrenheit, what should the mixed air temperature be? It probably should be 55 degrees Fahrenheit or close to it. But we're finding 70 degrees Fahrenheit. I think we're onto something here. I think we might have found a potential issue. The damper positions are not where they're commanded to be. The takeaway here is we can utilize the temperatures to determine if valves or dampers are stuck. So for instance, we would expect the mixed air temperature to be 55 degrees right here. These values of 100% outdoor air damper, return air damper at 0%, those are commands being sent to those damper actuators. Now you might have a failed actuator. You might have a broken linkage on a damper. You might have a 2x4 or a shoe jammed into your return air damper. And these are all things that I've seen before. So if anything, instead of sending a technician to the space to investigate too hot of a space, you could take 5 minutes, look at the building automation system and narrow in on the fact that we think it's these dampers over here back in the air handling unit, they're not operating as intended. Those are probably the root cause of this issue. All right, let's move on to troubleshooting exercise number 2. I'm going to present the issue and then allow you to pause the presentation to apply that 6-step methodical troubleshooting approach. Situation, it's March 3rd. It's 22 degrees Fahrenheit outside, and the space temperature is too cold. Pause this presentation, work through the methodical troubleshooting approach, refer back to the sequences of operation, as well as the key information slide that's been made available to you as well. Okay, welcome back. Let's work our way through it. Step 1, prerequisite. Know the sequence of operation. Done. Step 2, validate the complaint or observation on the BAS. So the space is too cold. So the complaint is the temperature in room 215 is too cold. Well, it looks like it's at 65 degrees. I agree. I cannot work too well at 65 degrees. Step 3, is the variable in question being controlled for? Yes, we know that we have a thermostat located in room 215, and we have a dedicated VAV box, which is dedicated to the temperature control in that room. Step 4, let's investigate that control loop. Step 4.1, is the set point appropriate? Set point 65. Wait a second, the set point 65 and the room temperature is 65. I would say that this air handling, or that this HVAC system is doing pretty good. It's maintaining the temperature at set point. But that set point obviously is not appropriate if you have people calling from the space saying that it's too cold. So the root cause here might actually be something associated with the zone mode. Because here we got the zone mode saying it thinks the zone's unoccupied. Now zone mode, depending if you have occupancy sensors or not, can be done in one of two ways. Maybe the zone mode goes occupied when an occupancy sensor triggers, and then it resets the room 215 temperature set point to something more appropriate, like 73 degree Fahrenheit set point. And then when the space is unoccupied, it sets back that temperature maybe to 65. Or you might have like a programmed schedule for this particular zone, where on the automation system, you say you have like a time and day schedule saying like this zone is going to be occupied from these hours to these hours, Monday through Friday. It's going to be unoccupied on nights and weekends. So maybe the schedule itself was set up inappropriately. So the key takeaway here is occupancy schedules set back room temperature set points to save energy when people are not there. But you got to make sure those occupancy schedules are correct. Otherwise, you could run into issues like this. Troubleshooting exercise number 3. Again, I'm going to present the problem and allow you to pause the presentation and work through it on your own. Situation, partial occupancy throughout the facility. The hot water system is seasonally disabled. So they shut down the boilers for the summer in this particular scenario. The issue was the space is too cold. Pause the presentation, refer to the sequence of operations if need be, and work your way through the methodical troubleshooting approach. And then hit play when you think you solved it. All right, welcome back. Let's work our way through this. Step 1, know the sequence of operation. I know it. Step 2, if possible, validate the complaint or observation on the BAS. Well, the complaint is that this room 215 is too cold. All right, room temperature is at 67 degrees Fahrenheit. Yes, that'd be too cold. I would not like that. All right, step 3, is the variable in question being controlled for? Yes, we know that room 215 has a stat and we have a dedicated VAV box which is performing the temperature control for that particular room. Let's investigate that control loop. Is the set point appropriate? Set point is 73 degrees. That sounds reasonable. Is the controller response as expected? Well, again, controller responds to air between temperature and temperature set point. So any difference between temperature and temperature set point, the controller is going to respond to that difference. So if we're 6 degrees below set point, we would expect the VAV box to be doing two things. For one, the airflow set point should be reset to its minimum value by now. And it is. The airflow set point is 130 CFM. And then the reheat coil should start to be modulating open to maintain space temperature in this scenario. Well, we must have been below set point for quite some time because the reheat coil is already 100% open. All right, step 4.3 is the manipulated variable as expected. So there's kind of two different manipulated variables here. Is the airflow really tracking on set point? Yeah, more or less. We're getting 5 CFM more than we wanted, but for all intents and purposes, we're basically tracking on set point. 5 CFM is not going to be a big difference here. How about, are we raising the temperature of the air going into the space? Because we should be with a 100% open reheat coil. Well, actually, we got to think back to the situation. We got to know that the building actually has the hot water system seasonally disabled. So yeah, we would be able to maintain temperature here if hot water was available, but clearly it's not. And that can be validated over here. Hot water supply temperature is at 76. That's like room temperature. The pump is off. Okay, so are we out of luck? Are these people just going to suffer because the boiler system is down for the summer? Well, it's 78 degrees outside, so I would say that there's probably something else going on. All right, so step 5, what other variable could be causing this issue? Well, let me see. We're getting minimum airflow into the space. It's not as warm as we want it to be because, you know, we don't have hot water available. But how cold is it then? Well, geez, it looks like it's 52 degrees Fahrenheit. So the supplier temperature is 52 degrees Fahrenheit. Okay, so that seems pretty cold. Let's take a look at that. Is that variable being controlled for? Step 3. Yes, it is. That's a controlled variable. Step 4. Let's investigate the control loops that are maintaining the supplier temperature at set point. Is the set point appropriate? No, it is not. That set point is 50 degrees Fahrenheit. We got the cooling coil wide open, we still can't even get there. Why can't we get there with the cooling coil wide open? Well, it's because the system wasn't designed to be pushing out 50-degree air. Again, the system was designed for the hottest day of the year to be putting out 55-degree air, right? So someone at some time had overrode the supplier temperature set point to 50 degrees. I suspect that a few months prior, they probably had people complaining of it being too hot in the space, so they lowered the supplier temperature set point to try and satisfy those complaints. Well, you should, on a supplier temperature set point, you know, you should never be doing overrides to override it below the design supplier temperature. So the supplier temperature set point was lower than designed for, and this resulted in comfort issues. We were overcooling the space. And energy issues, because now that increases the load on the chiller. The pump is running at full speed, so we're increasing pump energy. And if the boiler system had not been disabled, we would have had a lot of reheat energy wasted as well. What do I mean by that? I mean, we would have been paying to cool down the air to, say, 52 degrees Fahrenheit, and then we would have been paying to warm it back up to keep the space temperature at set point. Now, the hot water system is disabled in this case, so reheat energy waste is not necessarily a thing here, but as you can see that it could be. Okay, what's the major takeaway here? Lowering set points is a quick fix, and it's rarely the correct fix. Don't exceed design set points. Go and find the root cause of the issues instead. Troubleshooting exercise number 4. Situation, partial occupancy, other zones are unoccupied, and you have a hissing sound coming from the diffuser. Pause the presentation, work through the methodical troubleshooting approach, and I will give you a hint here. Step 3, look at step 3.1. All right, welcome back. Let's work our way through this. Step 1 of the methodical troubleshooting approach. Know the sequence of operation. We know it. Step 2, validate the complaint or observation on the BAS. Well, the complaint is a hissing sound coming from the diffuser. Now, most HVAC systems don't have some sort of like sound device measuring sound levels. So can't really do that. However, let's just press on to see if we can't figure this out anyways. Let's move on to step 3. Is this variable, this loud noise? Is it being controlled for? No, it's not. Well, how about step 3.1? Is there another variable that would kind of correlate to this sound? Well, I would think that if you're pushing air at high velocity through a restricted orifice, that could possibly create a hissing sound. All right, so let's look at airflow. Step 4, let's investigate that control loop. So the airflow right now for this space is 1000 CFM set point, and we're at 1020 CFM. So we must be controlling well, and yeah, we're controlling well to space temperature. Well, 1000 CFM, that's in between the minimum and maximum airflow range for this particular box. So I don't think we have like excessive airflow. Is there any other issues? Step 5, what other variables could be causing this issue? Let's just kind of look elsewhere in the system and see if there's anything that seems out of place. Supplier temperature is at 60 degrees. Okay, apparently that's okay because we're maintaining temperature right at set point. The supplier pressure is at 3.2 inches. Well, wait a second. Supplier pressure set point is at 1 inch. So we have over 3 times the static pressure in the supply duct than we intend to have at this case. So let's investigate that control loop. That is a controlled variable. The supply fan modulates the speed to maintain supply air static pressure at set point. Is that set point appropriate? 1 inch. Now you may or may not know this, but yeah, 1 inch, that's a reasonable value for a set point. And I knew this is actually a real world example from a building I was troubleshooting, and 1 inch was a pretty appropriate set point for this system. Step 4.2, is the controller response as expected? So if we're way above static pressure set point, we would expect that supply fan to start slowing down. And we know from the sequence of operations that the fan will modulate to maintain static pressure at set point, but will not be allowed to operate below 15 hertz frequency. Well, hey, we're sitting at 35 hertz frequency. Something's wrong there. So the control response is not as expected. The VFD can't slow down anymore to meet the supplier static pressure. Too high of a minimum speed setting must be programmed in. The VAV box damper is near close to dissipate this excess pressure. So the fan can't slow down, so it's pushing more pressure into the supply duct, and the VAV box damper is compensating by pinching off even more to maintain its airflow set point. So now you have 1000 CFM going through a nearly closed VAV box damper, which is creating this hissing sound to come out of the diffuser. So the takeaway here is know how to recognize minimum settings and know when they're inappropriate. So for instance, if you look at a frequency on a supply fan or a return fan or on a pump, if you're looking right on a VFD itself, and you see the frequency in hertz is 0.00 at the end of it, 0.00 is rarely maintained. Usually the hertz is fluctuating quite a bit. So it's only maintained unless it's only maintained at 0.00, some value 0.00, if we're at the minimum or maximum speed settings. So in this case, this is a real world example. We had just found that the minimum speed setting had been configured incorrectly. And once we adjusted that, we were able to track on set point more appropriately, and that hissing sound disappeared. Last troubleshooting exercise. January 3rd, 5 degrees outside and cloudy, pretty cold. And the space is also pretty cold. Pause the lesson and work through the 6-step process. All right, welcome back. This is the last exercise. Let's see how you did. Step 1, prerequisite, know the sequence of operation. I hope you know it by now. Step 2, if possible, validate the complaint or observation on the BAS. Space is too cold. Let's look at room 215 temperature. Looks to be 65 degrees Fahrenheit. Yes, I would say that the space is too cold. I could not work at 65 degrees Fahrenheit. Step 3, is that variable being controlled for? Yes, we know that room 215 has a thermostat and we have a dedicated VAV box with some components in it dedicated to the temperature control of room 215. Step 4, investigate that control loop. Okay, so we're at a temperature of 65. We want to be at 70. What would we expect? Step 4.1, is the set point appropriate? 70, yes. Step 4.2, is the controller response as expected? Well, I would expect that the airflow should be at minimum flow and the heating coil should be modulating open. In this case, yes, the airflow set point has been reset to its minimum value and the heating valve is already at 100%, so we must have been below set point for quite some time. All right, is the manipulated variable as expected? So there's kind of two different manipulated variables here. The first one would be airflow. Yeah, the airflow is basically tracking on an airflow set point. But on the heating side of things, as we open this valve, we would expect the discharge air temperature to rise. Well, we don't have a discharge air temperature sensor on this particular VAV box. So we don't know for certain. But let's look at other things. Well, we have an inlet supply air temperature of 60 degrees. And if we got pretty low airflow and we have 100% open coil, we should be able to provide enough heat. Now maybe let's look into the hot water system. So step 5, what other variable could be causing this issue? Well, is the hot water system operational? Yeah, the pump's operating 100%, set point's 120, and hot water supply temperature is 120. Okay, so let's look at that particular control loop. Step 4, is that set point appropriate? Well, January 3rd, 5 degrees outside and cloudy, that's like a design day. And as you know, this system was designed to provide enough heating when the boiler system's operating on a design day at 160 degrees Fahrenheit. So I would say no, that hot water set point is inappropriate. This is a design day and the hot water supply temperature set point is set lower than the system was designed for. And the major takeaway here is that reset schedules, resetting the hot water supply temperature set point, they often make sense, especially for like condensing boilers and things of that nature. But you got to ensure that the design temperature is maintained for those design days. So at a design day like this, we should be operating at 160 degrees Fahrenheit. All right, that's the end of our presentation. I hope you enjoyed it. Again, I'd like to thank our online sponsors for making today's webinar possible. Feel free to contact me if you have any questions about this presentation. My information is provided there. Just a reminder to complete the evaluation form that you will receive in the email following this webinar. And lastly, be sure to join us for the remaining webinars in this series. On July 21st, I will be presenting a live webinar titled Part 2, Make Better Use of Trend Data. And then again on August 4th, I will be presenting another live webinar, Part 3, Cost Benefit Analysis, Quantifying Energy Conservation Opportunities. Visit slipstream.org for more information on those. Thank you.